All right, let's move on to example beta, I guess. Since we did example alpha, let's follow suit here. So in this example, let's say we're like designing a can, right? Just a simple can. And I know not all cans look like this, and some of them have like those like ridges on them and things like that. But we're just assuming that we have a nice looking can here, and we've been tasked to design a 1 liter oil can. The oil is kind of irrelevant, but it's saying to kind of like minimize. You want to minimize the like kind of you want to minimize the volume for this one, right? Because if you think about it, right, when we are constructing things, we want to use the least amount of material, right? So if like we're talking about a can, usually they use like aluminum and stuff like that to create these cans, and then they recycle them and all that stuff. But what we want to do is minimize the amount of, let's say, aluminum that we have to make sure that we can manufacture the most amount of cans that we can get. So a couple things that we're going to need, right? First of all, well, we need to know what the volume of this right cylindrical right oh my gosh right cylindrical I am blanking on the word cylinder, right? No, right circular cylinder. Oh my gosh, that was confusing. Right circular cylinder, that's what this thing's called, right? And if you don't remember, the volume is actually pi r squared. It's the area of the circle times the height of however tall the can is, right? So that's the volume. But if we're talking about least amount of material, right? Well, if you think about it, when we create a can, we what we're really doing is you can actually like unfurl the aluminum, right? And actually, you can if I were to cut the can open, right? Like it would unfurl, the side piece would unfurl into like a rectangle, and then you'd have the top piece and the bottom piece, if you can kind of imagine that, right? So what we're talking about here in terms of the material is surface area, right? And the surface area of a right circular cylinder is it's going to be two circles, so it's 2 pi r squared, plus the area of the rectangle. Well, the area of the rectangle is going to be the circumference of the circle times the height, and circumference is 2 pi r. So there we have it. We have these two formulas that we have here, right? And we're going to use what we know, right? It's said to design a 1 liter oil can. So why don't we do this in centimeters, right? For funsies. So 1 liter is equal to 1,000 centimeters. Right. So 1 liter. I guess we're talking about cubes, right? So here we go. So here we go. This means, so the volume we want, the max volume that we can hit is 1,000. That's kind of like our roof. That's the thing that's stopping us from kind of like, that's the thing that's telling us that we cannot go beyond 1,000, right? Because let's say that's just how much material we have to play with, right? So once again, this is a minimizing problem. And what we want to do is we want to minimize the surface area, okay? We're not minimizing the volume. I know this is a little confusing, right? The volume is more of our, it's a word called constraint. I don't know if I'm going to mention this in class. So it's more of a constraint telling us what we're not allowed to exceed or go under in this case, right? But the problem is asking to minimize surface area, essentially, because it's asking the least amount of material that we can use, right? So here we go. We're going to try to relate these two things, right? So if we're trying to minimize the surface area, this is the one that we need to derive, okay? So we need to first use our volume function, right? If this is 1,000 centimeters, I guess centimeters cubed, right? Well, then what we can do here, is solve for, because right now our equation is in terms of two variables. And that's not really useful to us. It needs to be in terms of one, right? We want to derive in terms of r. So what we're going to do here is we're going to come up with an expression using this guy right here, so that we can plug in for h. So that means we got to solve for h here. So h is going to be 1,000 over pi r squared. And what we're going to do with this h is we're going to actually plug it into here. Oh, whoops, that's a little ugly. We're going to plug this h into here so that we have a function. Usually functions are denoted with, I'll just do s of r, right? So s for surface area. In terms of one variable, in this case it's r. So we're going to rewrite this 2 pi r squared plus 2 pi r times 1,000 pi r squared. And this is it. This was the hard part of the problem, right? It's the hard part is to figure out, well, which formula, especially when you're dealing with multiple formulas, which formula is going to be the one that I have to derive, right? And then I have to make sure that the formula that you're given is one that's in terms of one variable, right? So I know it's a lot of things to consider. So once again, don't get mixed up with your constraints and what it is you're trying to optimize, right? So just keep that in mind. So here we go. My S of R now is, I can clean this up a little bit. This is 2 pi r squared plus 2,000 pi over, oh wait, no, the pi's cancel out, right? Cool. 2,000 over r. Look at that. And now I have a function that I can derive. I can ddr this because I want to set this equal to 0 because I want to minimize this, and I need to check if the critical point that I find, one, fits in our domain, and two, goes from, well, if we're trying to minimize, right? Minimize is when you're trying to go from down to up. So this critical point needs to go from negative to positive. Unlike the first example, when we were trying to maximize, that's going from positive to negative, right? So here we go. I'm going to derive this bad boy. This looks like 4 pi r. 4 pi r, just making sure I'm doing this right. Plus, oh no, there's a thing in the negative. So that should be, it's going to be minus 2,000 r to the negative 2. And it looks like I need to set this equal to 0. So 4 pi r minus 2,000 r to negative 2 is equal to 0. And solve this. So it goes 4 pi r equals 2,000 r to the negative 2. I multiply both sides by r to the negative 2. No, I just multiply both sides by r squared. And then this will be r cubed is equal to, I'm just going to do some quick math here, 500 over pi. Just want to make sure I'm doing this right. And then cube root it. And if you use your calculator to cube root this, you can pause the video if you want to do the calculations on your own or whatever. But if you cube root this, you get approximately 5.42. Oh, they really don't like to round to 3 decimal places, but anyways. So you get 5.42, and this is, remember, this is your critical point. We need to kind of check that the function actually goes from negative to positive at 5.42 on my derivative function, right? So if you sketch this thing, I'm sorry, not sketch, if you graph this in Desmos or in your graphing calculator, you're actually going to get a graph that kind of looks like this, and then this is the 5.42 number, and you see that the values on the derivative actually go from negative to positive. Oh wait, no. I'm sorry. On the original function, the slope goes from negative to positive at 5.42. Right? So so not this one. This one. If you graph this one. If you graph S of R into your function, you're going to get something that looks like this. It's not perfect, but you see that the slopes are going from negative to positive, which confirms that this is indeed a minimum. So what did we just figure out again? We just did so much. It's so easy to kind of get lost in the sauce here, right? We found the radius, the optimal radius, that will create a volume of, what is it? At least 1,000, no, at most 1,000 centimeter cubed can. Did I do that right? I think I did that right, right? So if you think about it, if you take this value, if you don't believe me, if you take this value and you plug it into the volume formula, which is pi r squared times h, which is really pi r squared times, what was it, 1,000 over pi r squared? Oh, well, duh. But yes, if you take this r value and plug it in, you can find the h value, the height of the can that you can create, right? So, so what was I saying? So this is going to be like that 5.42 squared thing. If the max is 1,000, you can get, what is it here? 1 second. You would get, h is approximately, I'm just using the book values, 10.84 centimeters. So once again, it kind of depends on what the question is asking for, right? If the question is asking for, what is the radius that will minimize this? What is the height that will minimize this? You have both answers here. This is the height, this is the radius, and yeah, that's pretty much it. Oh, the question might also ask, I'm sorry, what is the surface area that what is the minimum amount of surface area that you can get, right? So you would just use the surface area formula, which is once again 2 times pi r squared plus 2 pi r h, right? And then you would just plug in these values. Where's my r value? It's like 5.42, and you plug in 5.42 to figure out the least amount of like aluminum you would need for this can. All right, so there it is. 2 examples for you. Definitely look these through. If you have questions on how I did anything, please just reach out. I will Zoom with you, and hopefully it'll be better. All right, guys, take care.